What's going on, everybody? This is Mr. Diamond here, and we're going to work out our example problems for the velocity and speed and acceleration sections of our notes here. So I've got the first example problem that I had. I've already gotten a little sketch for it. You're going to get used to me having some really bad drawings. Drawings are not super required for this portion of the class, like this early stages of it, but in later stages it is very important you get pictures and you have them to be able to look at and figure out what's going on. So I'm going to be drawing pictures as we go as much as possible just to make sure that we are in the habit for it. Also, I apologize, I had to rearrange where my mic is because of the setup here. I'm at school instead of at home, so it's not in my normal position. I might be a little louder. I apologize if that's the case. And also, if I bump this, it's going to shake like the whole thing. So I also apologize for that. But in our first example, we have a runner who is moving along a conveniently placed x-coordinate grid. They are starting at 50.0 meters, and they're ending at 30.5 meters. And that journey takes them 3 seconds. And we want to know what is their average velocity. Now, we know from earlier that our velocity is equal to x2 minus x1, or in final position minus initial position, divided by time, the final time, minus the initial time. So what I like to do first, again, is I like to list out everything we've got so we can just see what it is. So our time we've already got up there. Time 1 would be just 0. The clock hadn't started yet. And then after we know the timer started, our T2 is going to be 3 seconds. Our X1, our initial point, is 50 meters. And our X2 is 30.5 meters. So now we've just got one-to-one. We've got the exact setup we need to be able to solve this example problem. Velocity equals, and make sure that you've got x2, the 30.5 minus 50. Make sure you put them in that order. And then it'll be 3 minus 0. I actually don't think it was 3.0. I think it was just 3. But for sig figs in this one, we'll not worry about that too much. Let's go ahead and put equals, and let's enter this into our calculator. 30.5 minus 50 divided by 3, we get negative 6.5. I actually am going to change this to 3.0 in the notes, and I'm actually going to do that right now before I forget. I'm trying to get better on the sig figs. A lot of the questions did not actually have good sig figs in their questions, so I'm having to kind of fix them as I go. Now, this is negative 6.5. This top number was a meter. This bottom number was a second, so it's meters per second. We have a magnitude, and then we have a negative, which is a direction. So we don't actually have to worry about putting like east or south or north or anything like that, because our negative tells us that since this was a normal x coordinate, that the fact that he's moving backwards, the fact that he's moving that direction, means that his velocity must be negative. Okay, that was a pretty easy example. We're going to go ahead and move to our acceleration example, which is also going to be pretty easy. Things will get a little bit more complicated in the later part of this. Let me find... There it is. Okay. Now, prepare for what some people last year found to be the funniest thing they'd ever seen on the planet, at least in this stage of this class, which is you will get to see me draw a lot of cars that I am very bad at drawing. Let me make sure I know where my kind of window that I'm looking at is. So, okay. So we've got a car. I draw my 2 tires. Draw this bottom piece here. It's going to go up. There's my car. This is the reason I'm not an art teacher, guys. I apologize. Car accelerates down a straight stretch of road. So it's going to go from this direction. And I'm assuming that because it says it's going from rest to 75 kilometers an hour. That's a positive number. So I'm going to assume because it's a positive number that it's going to the right. 75 point, or nope, no 75, just 75 kilometers an hour. And it's doing that in a time of 5.0 seconds. What is the average acceleration in meters per second squared? Now, in this question, I just said the car accelerates. I'm going to amend that to make this make a little bit more sense. We're going to also say the car accelerates uniformly. I didn't specify that in the original version of this, but I just typed it on there, so now it exists, and it always exists based on, you know, at least your understanding of this stuff. Whenever you see it, it should have already existed. So now we're going to want to use our acceleration. And that'll be more relevant for one of the later questions. We'll come back and look at this. Acceleration is equal to, or it should be lowercase a, my bad. Acceleration is equal to the change in velocity over the change in time. I'm going to try and get better at my t's as well so they don't look like plus signs. So I'm going to try to make this little kind of squiggle at the bottom just to make them look a little bit more like t's instead of crosses or plus signs. So this is going to be v2 minus v1 over t2 minus t1. Okay, for our velocity, our initial velocity is, well, it says it accelerates, make sure I got there, uniformly going from rest. So from rest, 0 meters per second. Now the lights have gone out on us. Oh no, what darkness falls upon us? Oh, there we go. Okay, it's back. I apologize for that blinding flash. Let me try to center this a little bit more. So our V1 is 0 meters per second. Our V2 is kilometers an hour, because we want to be consistent. 75 kilometers an hour. And then our T1 is 0. Our T2 is 5.0. So let's convert this 75 kilometers per hour. This would also be 0 meters per second. Converting that is not going to radically alter that number, but let's go ahead and we'll have to convert that in our problem. So what I'm going to do is I'm going to do acceleration equals, I'm going to put in parentheses, because in physics, with how many calculations we do, we like to try to do this all in one go. I'm going to do 75 kilometers, 1 hour, one kilometer is 1,000 meters, 1 hour is 3,600 seconds. My kilometers will cancel, my meters will be there. My hours will cancel. I'll be left with seconds. Then it's going to be minus 0 meters per second over 5 minus 0. And sig fig wise, it will be technically 5.0, but it's 5 minus 0, so it's going to be 5.0. So I'm going to go ahead and plug this into my calculator. The way I'm going to do that is we're going to go 75 times... put it in parentheses, 75 times 1,000 divided by 3,600, close parentheses, divided by 5. And then both of our numbers that we had 2 sig figs, so my answer here would be 4.2. We'll have meters per second, and then on bottom is another seconds, which is why it becomes seconds squared. So my answer for this one would be the average acceleration. And again, he might be going way faster at the beginning, he might be going way slower at the end, or it could be vice versa. All we care about is what the average is, and the average in this case is that over the course of this, on average, he was increasing his velocity by 4.2 meters per second every single second. And that's why it's meters per second per second. Okay, I hope those examples make sense. I apologize if I stumbled through that last part a little bit. The setup here is a little bit awkward, and I'm paranoid about bumping into things. So it's also hard to pull things up on the screen. If you have questions or you want me to re-explain these, or if you want me to work out a different example, let me know. If you don't have any questions, then I guess I did my job. Yay me. Look at me go. Hope you have a great rest of your day. This is Mr. Diamond signing off.